Welcome to the Cognitive Informatics Seminar. And today's presenter is Steve PIANTADOSI. I think those of you who are here from distance have already seen his abstract and his title. I'm going to present Steve in French first, and then I'm going to present him more briefly in English, and then I'll pass it to him. Steve, welcome to Montreal, so to speak. Can you hear me all right? Okay.
Yep, great.
So, your title in French is Les règles et le neurone, et qu'est-ce qu'il y a ensuite? Qu'est-ce qui arrive ensuite? Steve PIANTADOSI est professeur au département de psychologie à l'Institut des neurosciences à l'Université de Californie à Berkeley. Il dirige le laboratoire Kolala, right? That's the name. Kolala, computation et langage à Berkeley. Ses recherches computationnelles et comportementales portent sur l'apprentissage du langage et des concepts. Concept, je vais peut-être poser la question à un moment donné. I might ask you what you mean by concept at some point. L'évolution de la cognition humaine et le rôle de l'ambiguïté dans la communication. Dans sa critique de la théorie de grammaire universelle de Noam Chomsky, PIANTADOSI soutient que le succès des grands modèles de langage, LLM et LLM, remet en question la plupart des hypothèses fondamentales des théories linguistiques traditionnelles. You say standard linguistic theories. I assume what you mean is Chomskyan linguistic theories.
Yes, that's right.
Okay. Avec ça, je ne lirai pas le résumé, je crois que vous l'avez eu. I'm not going to read the summary. The title is Rules versus Neurons and What May Be Next. And Steve is at Berkeley in the computational and in the computation and language lab. And I want to welcome to Montreal, and I really look forward to I should add that he's already been by proxy here in Montreal because several of his collaborators participated in the summer school on a related topic. Steve has said that he's happy to take questions during his talk, but I will add, they involve a long discussion, a likelihood of a long discussion, leave it rather for after he's finished. But if it's something that about understanding or about something immediate, then go ahead. And in fact, go ahead without even going through me, because it's too difficult to manage all of this all at one time. So just chime in if you've got a question to ask. Steve, it's all yours.
Awesome. Thank you so much. And thank you again for the invitation to come talk. This is such an incredible group that you have here. So yeah, thank you. Let me share my slides here again. Okay, so you should be able to see that?
Yes.
Great. Okay. So I'm going to be giving a talk that's a little bit bimodal. You know, my lab, as you said, mostly works on language and concepts. And I'm going to give a talk about some about large language models. So what I see is some of the insights and things that we've learned about how to model language from large language models, especially in contrast to prior rule-based models. And then the second half, I'm going to go a little bit in the other direction, actually, and talk a bit about why, even though I'm not a huge fan of the kind of Chomsky-style approaches to grammar, why we might nonetheless think that there might be things like rules even inside of large language models. And I'll talk some about some of this work actually from the 1950s and 60s in computer science, which aimed to essentially rigorously establish when there were internal states to a system and how those states were related to each other. And if you think about applying those in the context of large language models or in the context of neuroscience, it may be that sometimes we can find things like grammars inside of these systems. And so I'd like to talk some about that in the second half of the talk. So I'll start just by giving a kind of overview of rules versus neurons and why we might want to think about both of them. I'll do a little bit of a case study of Chomsky-style linguistics. This is some papers that I've written recently on kind of that approach and how it's different from large language models, what we might learn from large language models. And then I'll focus in on an example of finding things like hierarchies or grammars based on this older work in computer science that, as far as I can tell, is not widely known in any of these fields, linguistics, cognitive science, or neuroscience. So I want to start just with the most basic kind of observation, something that's so obvious, I think, most of the time we don't say it, which is that the brain is really made of neurons. So if you open up a brain and you stain the neurons, you get pictures that look like this. And the key here is that when you do this, when you look in neuroscience, you don't see anything that resembles the kinds of constructs that we have in cognitive science or linguistics, right? You don't open it up and see grammars. You don't even open it up and see words or meanings or anything. What you open it up and find is kind of a neuroanatomy that is apparently very distributed and probably very noisy and probably very messy. So this means that there's a real disconnect, right, between cognitive science and neuroscience, in that they often use completely different terminologies. So cognitive scientists might be happy to talk about things like grammars or logics or number or concepts. But saying what any of those mean in terms of brains when you open them up like this is really quite difficult, I think. On the other hand, I also think that if you look at people's behavior at a high level, what you find is actually very clearly symbolic and involving things like grammars and abstractions like concepts. So here, for instance, is just a page from a famous math paper. And you can see it's written in language, which is discrete and symbolic. We can see that because of the words, right? And even the words are written, are made with symbols, right? So they're made out of letters or phonemes. This happens to be a math paper which is studying number theory, so it's talking about constructs which are very abstract, and it's using even mathematical language and mathematical terminology, which is an entirely different symbol system than the one that we have kind of naturally through language, right? You have to learn calculus or algebra or logic. And so it seems that people are able to create and internalize these kinds of other these other types of symbolic representations and symbolic systems. All of this is just to point out the contrast here, right? That somehow you have to get from the stuff on the right and end up with the stuff on the left. And I think there's, if you look across fields, there's kind of mistakes both ways. There's people in AI who think that the stuff on the left doesn't matter, the symbolic stuff doesn't matter because it's really all neurons. And I think there's also people in cognitive science who think that the stuff on the left can just be studied completely independently of the stuff on the right. And that may or may not be true. That's kind of a controversial argument often associated with Jerry Fodor, that high-level abstractions can't in principle be cached out in their neural basis. And I think that may or may not be true. I think for most people, we should view this as kind of the goal is connecting these, right, and saying how the stuff on the right can give rise to the stuff on the left. So this idea of there being symbols has been around for quite a long time in cognitive science and AI and logic. In fact, symbolic approaches trace to the very early days of logic, at least to Boole. So people are familiar, I'm sure, with Boolean logic, Boolean variables in computer programming, just trues and falses. And seems like almost trivial nowadays, I think, to think of, you know, logic made out of true and false operators for true and false values. But Boole, when he was working this out, he presented it in this book called An Investigation of the Laws of Thought. So he was really doing, you know, kind of proto-AI or proto-cognitive psychology and trying to think through what reasoning looks like and how he could capture reasoning in a system that had that was based basically in algebra. So he was borrowing algebraic notation and ideas from algebra, meaning symbolic approaches, and trying to use those to capture core kinds of reasoning processes. There's other people actually in the history of mathematics and logic who have tried similar things. So Leibniz tried to come up with a kind of description language for what he wanted to do was describe all scientific truths and be able to derive what was true and what was not true. Of course, people I'm sure are familiar with many of these other authors, especially from the early days of cognitive science and AI. People like Turing and Shannon and Newell and Simon, Fodor and Polishin. People essentially arguing for symbolic representations in cognition, and in some cases proposing computing systems, things like ACT-R or Prolog or Lisp, where symbolic components are really the core key pieces of these representations. Maybe the most well-known, I think, example of symbolic approaches is Chomsky, right, who argued for generative grammars in linguistics. Essentially, you know, starting one, I think, very powerful and popular approach to studying language at the same time as he started a powerful a powerful approach to computer science. So Chomsky's early work kind of elaborating different computing formalisms and different computing architectures and formalizing what kinds of problems they could and could not solve, you know, forms the foundation of the Chomsky hierarchy and a lot of theoretical analyses in computing today. So the goal of Chomsky's approach really was to find a small set of symbolic rules that characterize the grammatical sentences, hopefully in all languages. And this had several real goals or aspirations. One is that it would work for typologically diverse languages, meaning it should explain cross-linguistic patterns. He was interested, right, in finding universals of language, not just things which could describe, you know, one particular language, but really interested in human nature, right, and trying to use cross-linguistic comparisons in order to find, you know, discoveries about kind of formal computations that characterize human nature. Part of this is you know, finding hidden structure and properties in language, and I'll give an example of one of those in a second. But if you start analyzing grammars and trying to formalize them, you often find situations where the ground truth is like a little bit more complicated than you might think. Those complications have often been attributed in this kind of approach to specific details about how grammar works, and in turn how human nature works. And one of the other big goals was making sense of acquisition. So trying to say how you can take whatever the input is that kids get and arrive at these abstractions like grammar. And there's a lot of mathematical work in this tradition, essentially showing how that is a very difficult problem, or that might be a very difficult problem. Some claims of kind of impossibility, that it couldn't be done without building in substantial biases, which I'll talk a little bit more about in a few minutes. But generally, I see a lot of this work is really highlighting that there's a genuine inductive challenge there, right? There's a small amount of data that kids get, maybe 1/1000th as much as an LLM gets, and yet they're still able to take what they see and generalize, process, and produce totally new sentences that they haven't heard before. And so that's a really interesting inductive challenge from a learning point of view. And then the hope of this also was to make connections to biology, and to think about what it is that separates humans from other species. As far as we can tell, there's no other species that learn anything like the complexity of human language. And so maybe if we characterize the kind of core competencies of human language, we'll learn something about human nature and something about human biology ultimately. Let me just give a quick example of kind of work in this approach. So this is an example due to Hajras in the 1960s of coordination structure islands. So I can have a sentence, for instance, like Miro bought a shirt. And I can ask a question like, what did Miro buy? And here I'm questioning the thing in blue, so I'm questioning the shirt. Can also say Miro bought a shirt and car, and that's fine. And I can again question all of the stuff in blue. I can say, what did Miro buy? And the answer could be a shirt and car. But what's interesting and not obvious is that you can't question anything in a sentence. So for instance, I could say Miro bought a shirt and car, and now try to just question the stuff in blue. And I end up with a sentence that is very odd sounding and difficult to make sense of, like, what did Miro buy a shirt and? This is just an observation about language. It's just a fact that people don't like this last version, especially compared to the previous versions. And then there are attempts to explain this in theory. Many of the kind of Chomsky theories of this involve kind of imagining that the what word, in some sense, started out or refers to where car was in the original sentence and has to move out of there. And then there are syntactic or hierarchical features of sentences which block this kind of movement. So maybe conjunctions like and don't allow this kind of movement to happen, but you could move the whole conjunct like in the second example, or you could move something where there's no conjunction like in the first example. So you can kind of imagine trying to take sentences like these and patterns of grammaticality and ungrammaticality and figure out what the kind of restrictions are on what kinds of questions you can versus can't produce. I think most modern language models are good at this and probably don't have anything like these movement patterns. But I think it's worth highlighting that even if you can solve this problem in other ways, like this is a real problem for kind of all approaches and all ways of thinking about language to handle. There's many mechanisms that can do this, but the problem is there and an interesting kind of non-obvious one, I think, for all approaches. So let me start with just a couple positives of Chomsky's tradition here. So as in this example, there's it's motivated quite a few discoveries of subtle properties of syntax. So things like details of how you form questions or how you form agreement, these kinds of things where it's not obvious just in language. If you walked up and asked somebody who hadn't thought about this before, it wouldn't be obvious that there was anything interesting or complicated going on here. And I think it takes real, insight and work to discover these complications. In turn, I think relatedly, this tradition has also highlighted challenges of learning, especially statistical learning. So people, I'm sure, know this sentence, colorless green ideas sleep furiously, where the sentence was constructed so that each pair of words was meant to have about zero frequency. So if you look in a corpus, it's pretty rare to say colorless green because that doesn't really make sense. And it's also pretty rare to say green ideas or ideas sleep, so on. And so the fact that you can read this sentence and still judge it as grammatical was meant to illustrate that probability was not the thing that determined grammaticality. There was some other kind of more abstract level of analysis or understanding which determined what was versus was not grammatical. Of course, nowadays I think people can look at this and say, okay, yeah, that's true, but probably you can get to those higher levels of abstraction through some statistical learning, and I think that's almost certainly what large language models are doing. They're tracking statistics, but they're not doing just the dumbest statistics you could imagine, right? Tracking word-to-word transitional probabilities is the dumbest statistics you can imagine, and yeah, that doesn't work. But there's now lots of work in cognitive science and in linguistics showing that if you do smarter statistics, right? If you think of learners who operate over richer sets of hypotheses, you can learn abstractions like the abstractions required here of maybe part of speech categories or something like that. This work also, this tradition, I should say, has also encouraged cross-linguistic comparisons and documentation, which I think is a real positive. I'll just give one quick example of this. This is not from Chomsky directly, but from one of Greenberg's universals, is that in if-then constructions, the if part comes first. Okay, so across languages, this tends to be true that if they have an if-then construction, they put the if part before the then part. And that, again, I think is not obvious and takes real work to document across languages. And you might view that as some part of human nature, like there's something genetic in us that encourages that syntactic bias, or you might view that as a consequence of some other kinds of pressures that we face, perhaps pressures about pragmatics or information structure or something in sentences. But whatever the explanation is, that's still an interesting pattern that you can find cross-linguistically. And Chomsky's tradition also promoted tight links between language and other domains like logic and compositional semantics. So the kind of semantic work in this tradition, I think is very interesting for trying to work out logical meanings of things like function words, right? Like, what is the meaning of most is not obvious, and it's not something in the world, right? There's no most in the world. Instead, it's a kind of abstract logical relation. And I think good statistical learning models are able to acquire those, but like in the colorless green ideas example, maybe not the kind of most simple kinds of statistical learning models you could imagine. And finally, all of this has highlighted uniqueness of human language, right? So essentially all of these properties, including complicated syntax, are things that you really don't find in other species. And it's really an interesting mystery why you find them in humans and what it is in humans that supports this, what gives rise to these abilities. Sorry, my thing got messed up here, but let me go through a couple negatives of this tradition. So one is that it's been critiqued quite a bit actually for not having very many quantitative comparisons. So a lot of the arguments, including the coordination island I just showed you, right? You could present those arguments without experimental data, maybe just using intuitions or intuitions of linguists. And this is not great because ideally you would want your kind of empirical basis to be determined independently of the people proposing the theories, right? So you want some independent experimental test other than just kind of intuitions about it. There's also been arguments that while people have aspired to find universals, there actually haven't been that many universals which have been found in this approach. I mean, not that many pieces of human nature have been really justified in the way that many had hoped. My favorite reference for this is this Evans and Levinson paper, where they go through a number of purported universals, meaning things which linguists have claimed to be true in all or almost all languages, and show that there actually are exceptions basically to all of them. And so it's very hard to find things which are true across all languages and therefore very plausibly part of our kind of innate genetic endowment for language. Ted Gibson and I wrote this paper in 2014 trying to analyze the statistics of finding universals. And basically we argued that there aren't enough languages in existence to do reliable statistics about what's true in all languages, in all kind of logically possible languages. Chomsky's tradition has also engaged in what I think the best word for is bullying. So oftentimes people who have gone against the kind of primary claims in this tradition have received what seems to the outsiders to be a large amount of kind of hostility and pushback. People are curious about this. I'd refer you to this paper by Jeff Pullum called Dan Everett on Piraha syntax, which sort of tells the story of Dan Everett and Chomsky, Hauser, and Fitch's claims about recursion in human language. And Dan Everett was working with this group where he claimed that they didn't have recursive syntax and faced quite a bit of over-the-top attacks and criticism on what otherwise should have just been, I think, a pretty ordinary scientific question, right? Of what grammar, best describes this particular Amazonian language. But it happened to be one where the grammar that Everett was arguing was correct was one that contradicted some claims of Hauser, Chomsky, and Fitch. And as a result, he was quite harshly attacked, I think, for this. Another negative, I think, has been pseudo-formalization. So people will often write down grammars, or write down pieces of grammar or analyses of certain constructions, like the coordination island I showed. But there's not many implementations of kind of a whole theory. And for people who work in computation, right, I think it's a common lesson that many learn, including myself, that oftentimes when you go to implement something, you learn that you haven't been thinking about it precisely enough. You learn that there's some assumptions you haven't worked out, or that there's some components of your theory which don't mesh and don't fit together, and so there's something inherently which is self-contradictory. And it really makes you want to see full implementations of in particular, grammatical theories here, which are very hard to come by. Chomsky tradition has often been quite narrow on syntax, maybe also with some semantics, but there's no theories of other things like word meanings or construction, memorization, processing, memory constraints. All of these are kind of pushed on somebody else's, some other person's problem, which is fine. I mean, it might be that that syntax is like that, right? That syntax can be carved away from these other abilities. But I think one of the things that large language models show is that if you build in mechanisms for handling these other capacities, in particular for representing something about meaning and for probably dealing with constructions, which you could think of as like little memorized chunks of language. So like idioms are constructions, or common phrases are constructions that you memorize. If you build in mechanisms for handling those things, then you can build these really incredible systems for natural language. And so by expanding beyond just trying to model syntax, I think you almost will inevitably end up with a very different theory of syntax, and one that works quite well, at least in the case of large language models. And finally, there have been a lot of really bad claims about learning. So kind of mathematical formalization of some learning situations, claims of impossibility proofs, but the core assumptions that those analyses need often end up not being ones that match kind of human learning situations. So for instance, a lot of the work in kind of gold style learning assumes that parents are as additionally misleading as possible, right? That it's a worst case learning analysis saying in the worst case of the worst possible data, could you learn something or not? And that motivated quite a lot of theorizing. I mean, there's whole papers and books in kind of Chomsky traditions saying that because of these kinds of results, we know that language has to be innate. Because look, if parents were like this, then you wouldn't be able to acquire language. On the other hand, what's happened more recently, maybe in the past 10 or 15 years, is that people have worked out, in particular, Chater and Vitani have worked out very general learning results that essentially say, well, if you relax those assumptions and instead assume that parents are sampling data, from a distribution, then you can actually identify, the right distribution out of a space of all possible computable distributions, which is about as good as you could hope for. So there have been a lot of kind of bad ideas about learning. The end result of this is, well, I'll show you just a picture of a syntactic tree. So this is a syntactic tree for the sentence "John likes Mary." And you can see John likes Mary here is at the very bottom down here. And John likes Mary is embedded in 9 different levels. It has 9 different levels of syntactic embedding. This is Chomsky's minimalist theory in the early 2000s, roughly. And the reasons for this is, the reasons this come about, like each of these components, each of these 9 levels of embedding, is motivated by a specific family of arguments. But it's not kind of formally motivated, right? It's not saying, well, this is the only way things could work, or there hasn't been kind of rich comparison to different types of alternatives. Part of the intuition for why you get such a complicated structure for even a simple sentence like this is that if you think of the coordination island example, where I said, okay, it's like the WH word started out where the thing it was questioning was in the tree, and then moved out. Here you kind of have to have a whole bunch of different places for different things to move, or maybe things to move in complicated paths in various ways in order to derive different kinds of questions and other forms of sentences, like John was liked by Mary and these kinds of things. So some constraints of the theory end up giving rise to this extremely complicated syntactic structure that, I think most people, especially in neuroscience, would look at and say, this is just very implausible. Like, there's probably something very different going on representationally than what is proposed here. I should point out that this is not a parody. This is actually from a paper by Margolis and Lawrence on poverty of the stimulus, where they were arguing that people really should take these kinds of representations more seriously, and take in particular more seriously the challenges that they pose for learning theory. So how could you ever learn something like this? One answer, of course, that I think is provided by large language models is that maybe you don't need to learn something like this. Maybe if you think about the other types of kind of constraints and representations that are present in a large language model, but that don't agree with the kind of motivations here, you can do a pretty good job of processing sentences. Processing sentences like John likes Mary without having 9 levels of recursive embedding there. Okay, so all of this brings us to large language models, which I think have really key differences to Chomsky-style linguistics. I wrote a paper about this a couple years ago, which has had a number of replies actually in the questions. Some people asked about this. So there's, I don't know, 5 or 10 different papers replying to mine, and then I later added a kind of postscript onto my paper that was replying to the replies. So if people are interested in those, all of that is in the paper. I'll highlight just a couple of key points here. One is that LLMs really embrace probability, information, prediction, and data. And this is in contrast to Chomsky's approach. In fact, Chomsky said in the 60s that probability had nothing to do with grammar. And that's a view that he's maintained since. So he was saying it a few years ago in response to large language models and GPT and these kinds of things. The sense in which large language models embrace probability is that you can think of them as having some huge number of internal parameters. So billions or hundreds of billions of internal parameters, and those parameters are set in a way so that the large language models predict language as good as possible. So as good as you could possibly do given their data. They're trying to make accurate predictions about language, and one way to kind of think about what's happening there is that they're configuring their internal states in order to match the empirical probabilities. And critically, right, this is not empirical probabilities like, pairs of words in the colorless green ideas example, but probabilities that take into account a large amount of context, right? Maybe thousands of words previous could influence the probability of the next thing you're about to say. And large language models, essentially try to model that. So they try to come up with at least some approximation of how all of the previous contextual information matters. Part of this, part of what makes them successful, I think, is that because they have so many parameters, they're actually able to memorize quite a bit. So this is behind, for instance, a lot of these recent lawsuits accusing AI companies of violating copyright, right? Those come about because the AI companies have trained these language models on copywritten texts. And then part of what the language models do is memorize chunks of that text. And so if you query them in the right way, you can often extract, just memorize chunks of copywritten text. For linguistic theory, though, independent of all of the copyright issues, this very much matches an alternative approach to Chomsky's called construction grammar, where essentially what is proposed in construction grammar is that learners and language users acquire or like memorize pieces of strings, maybe which include slots in them for other content. So here's an example: the more you X, the less you Y, right? That's not one verb or one sentence. It's kind of one chunk that includes, a bunch of different grammatical pieces and grammatical categories, and it has these slots X and Y that might be filled in with different things in different contexts. And this has, I think, always been a kind of mystery for language learning. How is it that if you think language learners are figuring out the rules of grammar, that's fine, but that never explains how it is that people know this as a kind of coherent chunk of language. And I think large language models have figured out one way of doing both of those, of figuring out kind of general rules of language, as well as allowing themselves the ability to memorize chunks when it's needed. I forget the exact numbers on idioms, but there's tens of thousands of different idioms that people know, which are, chunks of language, chunks of multiple words where the idiom has a different meaning than something than what you would expect based on the words in the idiom. And so that essentially has to be memorized. So people have to be able to memorize tens of thousands of chunks and pieces like this. And large language models, I think, have figured out how to do that, and moreover figured out how to do that only from trying to fit probabilities, which is amazing. A third piece, a third real positive, this is in contrast to most linguistic theory, I think, is that large language models really handle lexical semantics. So one of the key starting points for building modern large language models has been kind of initializing them with representations of some of the word meanings. So you take one of these 2013 era models of lexical semantics that says each word is some vector, and we'll try to make vectors that predict where words are used. And so chair is some vector, and table is some other vector that maybe is similar in some ways, and dog is another vector that's completely different from both of those. And you initialize the kind of internal states of these language models with lexical semantic representations like those. And then when they're fitting parameters, they're maybe allowed to adjust them in some ways. But it's really critical in prediction that you know something about meaning, right? Because if you're really trying to predict upcoming linguistic material, it really helps to not just treat things as abstract, parts of speech like nouns and verbs, but to know which nouns and also something about those nouns, like what other nouns that they tend to co-occur with or what kinds of verbs they tend to co-occur with. So most theories of grammar try to parse all of this away, again, using maybe the colorless green ideas kind of motivation, right? Where there what seems to matter is not the lexical meaning of those words, but just their kind of abstract part of speech category, like is this a noun, an adjective, or a verb? And I think as a result, theories which don't track lexical semantics just can't do as good of a job at prediction, right? Because prediction really does depend on meaning, or at least kind of approximate representations of meaning here. And finally, they're able to take that, so to take the lexical semantic representations and integrate them with the memorization and the kinds of generative rules that they've learned. So I see, modern language models is really putting all of these pieces together in a way which is kind of hard to imagine exactly how to do. And that's, I think, why combinations of these have really eluded linguistic theory until large language models. So I trace actually these kinds of ideas, so the importance of prediction and representations of semantics and things, back to this paper by Jeff Ellman in 1990, which I think really set the foundation for all of this modern language technology. Ellman was really ahead of his time here. Basically, what he did is come up with a toy grammar, so just a small kind of approximation to English grammar. And then he had a simple recurrent network try to predict the sentences from that grammar. And like a large language model, right, this neural network configured its internal representations in a way where it was able to make as good of predictions as possible. And what Ellman found actually is that when you do that, you end up with representations which map onto things that make intuitive sense for linguistic theory and for his particular grammar. So what this shows is just a hierarchical clustering of the internal word representations that his model learns. So if things are closer together, like bread and cookie, they merge together in this diagram very quickly, then those have very similar internal vectors. But if I compared bread to boy, those merge together much further, so right here. And if I compared bread to eat, those merge together much further, like right here. And so the further away the path length is in this diagram, the further away the vectors are. This is just a way of kind of visualizing vectors. And what Ellman found is that this neural network would organize itself to mirror some of the key properties in the grammar. So for instance, you can look in here and find clumps like the animate nouns: mouse, cat, dog, monster, lion, dragon, woman, girl, boy, right? All of those are things which are animates and which will tend to be the subjects of sentences rather than the objects. These are things which tend to be the objects, so things like car, book, rock, sandwich, cookie, right? A sandwich never does something in a sentence. And then if we go to another cluster like these guys, right, you can see at the very top that there are all of these things are verbs, and all of the verbs are represented in a different way than the nouns. So this is like a little kind of glimpse of proto-semantics or something inside a small neural network like this, which part of Ellman's point was that all of this was just derived through prediction. So the neural network is configuring itself to predict well, and when it does that, it arrives at these abstractions that we think about, right, like nouns versus verbs or different kinds of nouns. And it arrives at those abstractions because those abstractions are specifically useful in prediction, right? If you're going to predict the next word, it really matters whether the noun you just heard was an animate noun versus an inanimate noun. There's a more general idea here, which I think is the kind of right metaphor for thinking about large language models, which is that of emergence, right? So the idea of emergence is that you don't necessarily build in the principles that you think are the true high-level description of a system, right? That's kind of what's going on in Chomsky-style approaches to language, right? People are positing specific high-level rules about syntax. Instead, what you build in is something low-level, and the high-level rules then emerge out of that. So they come about through some learning process in conjunction with the particular architecture and principles like predict well that you've built into that architecture. So I think that this is a Elman's example is a little example of emergence, and large language models are a really big example of emergence. How you can get really rich semantic and linguistic knowledge if you build just the right kind of neural network and then give it sufficient data. I'll just point people in case you're interested. I know this was one of the suggested papers. We recently wrote a collaborative paper. This is basically everybody in my lab got together and wrote this paper on concepts as vectors, essentially arguing that this view of concepts, right, that you get out of large language models or that you see in neural networks like this is a really, really good one. And in particular, it's a kind of representation of concepts that seems to do most of the things people want concepts to do in cognitive science. So it seems to handle rules, it can handle gradients, graded category membership, it can handle things like hierarchies. And I think, interestingly and surprisingly, there have been these cases in the study of concepts like ad hoc concepts, which are, things you just create on the fly. So, items you would take from your house if it was on fire is an example, right? And that's a collection of items that you can arrive at through a linguistic description like the one I just gave. And large language models, I think, show one way how you can form representations of concepts like those just as vectors, right? Those just correspond to some particular activation pattern. It's the activation pattern of that sentence. But large language models can reason about those kinds of items and tell you what items are likely to be in ad hoc concepts and things like that. So we basically argued that there's all of the kind of core criteria, core properties that people have wanted out of concepts are things that mostly recently others have been able to show how you can get out of vectors.
Steve,
yeah.
You said that you would accept questions during the talk, and I promised you this one. It's fine to say that concepts are vectors. I know what vectors are. And so now I know what X is. X is vectors, but what did you mean by concepts?
Yeah, I mean, I don't think there's a great kind of formalization of concept. I think of it more as an intuitive concept, as an intuitive thing, which in the simplest case, you maybe whatever word meanings are is an example, or whatever our internal representations are made of for abstract categories. I don't know, maybe those are not satisfying definitions to you, but I was going more of a usage-based theory on how people tend to use this term in cognitive psychology, for instance. So most words will have an associated concept. There's certainly concepts that don't have words, but probably are internal representations that you can think about and manipulate and do things with. Yeah.
I reserve the right to bring this up in the discussion.
Yeah. Okay. Great.
Okay.
Great.
Hang on. There's one other one. Mathieu, it has to be short.
Don't worry, it's going to be short. I'm just confused about one point. If the concepts are intuition-based, like there's no formal definition, does that go at like what you talked about for Chomsky intuition, where some reasoning that people said, we formalize it all, it was intuition-based? Aren't we just going to circle it to the same issue that we had previously?
Okay, question posed.
Yeah, so I certainly think in science you need to deal with intuitive concepts. So many of the things we try to do science about are ones that we don't have precise definitions of, and part of doing science is trying to come up with what the precise definitions are. I think of concepts like that. I think there's lots of debates in philosophy which kind of ground out in this problem. I mean, many philosophers have thought this as well, right? That there's our concepts are fuzzy enough that that often leads to considerable ambiguity about what it is we're arguing about and what data could tell us whether theory 1 or theory 2 was true. I think in the Chomsky case is slightly different because they were proposing formal systems. So they're saying, like, here's a proposal about how the grammar works, and maybe this, this is the kind of grammatical structure, and this part moves around to this other piece or something. And there, it's almost it's almost formal enough to be implemented and checked, but rarely ever is. So that was the critique there. But here it's a case where there's some intuitive thing that we think of like concepts, and there's a real challenge in formalizing them, like many other intuitive concepts we have. So our proposal here basically looks like this, that there's a kind of high-level concept vector, which is something that can be projected down into various tasks. So if you judge similarities, that's one kind of projection. If you ask people about features of objects, that's another. If you ask them for categories, that's another. If you ask them for definitions, that's another, right? And this is one of the non-obvious ones, that a vector can be converted into a string of words. That's something that large language models have shown, or descriptions or whatever. And so you can imagine that if this is a view of concepts, what happens when you have the dog concept here is that you get data from multiple different tasks. You get data, people telling you, oh, it's kind of like a cat or whatever, or it is alive. That's one of the features, or it is an animal. That's one of the categories. And as a learner, you get data from multiple sources like this, and you adjust this vector in order to do a good job on all of the tasks simultaneously. And so that's one kind of formalization maybe of what a concept is. It's the kind of shared information across tasks, and it just so turns out that vectors can seem to do a good job of that. I'll go just sort of quickly through the relationship between, this is also relevant to some people's questions, the relationship between this view and kind of views based on reference. So a lot of people have the intuition that meaning requires external reference, that there's some in order for something to be meaningful, it has to pick out some particular thing in the world, and there maybe has to be some kind of important causal connection between the internal representation and the thing out in the world. And this is something that Felix Hill and I became interested in a few years ago, and basically wrote out a longer argument arguing that this view of meaning as necessarily tied to external referent missed a big part of the picture. And I'll just give a couple of quick examples from this paper if you're interested. One is that many concepts have no reference to the external world. So you could think of function words like to or is or many. Those are kind of, those do an abstract syntactic thing, and in a large language model, those guys all have vectors, but their vectors are primarily about kind of manipulating the other pieces of a sentence. You can also think about non-function words, but ones which are very hard to tie to any external reference. So justice, for instance, has a meaning, but it's hard to point to the world and say justice. Or wit, I think, is kind of similar. Dragon is just imaginary, right? There's no thing out in the world which is a dragon. There's lots of words or phrases we know which have no possible reference to the world. So an imaginary bicycle, right, is by definition imaginary, or a perpetual motion machine, right, is something which we know can't exist. And even for ordinary concepts, like we likely haven't even considered all of the possible reference. So we gave this example of a pair of shoes made out of eggplants, and you could look at a pair of shoes made out of eggplants and say, oh yeah, those are really shoes, but they're made out of a physical thing which you haven't encountered before. And in that case, what that illustrates, we think, is that it's not the physical stuff which is determining the concept, right? It's something much more abstract and internal that determines whether something is a pair of shoes, that maybe has to do with how and why it was made, or what kind of function it's serving, and so on. And so instead, we argue for this view of kind of meaning through conceptual role, which we think of as really dependent on the relationships between parts of meaning, or relationships between words and concepts. So we give this example of a postage stamp, and say, oh yeah, a postage stamp is something you pay for, and you put on a letter so that the letter will be delivered by the government. That's some kind of definition. But critically, like that definition is built up out of other pieces, and the definition of a postage stamp therefore depends on all of those other pieces. So postage stamp is interrelated with your concept of payment, or your concept of government, or your concept of letter, and those interrelations are all internal kinds of relationships. One way you can see this actually is that if something changes, so for instance, if we develop a new form of payment, like we develop credit cards or whatever, then you can pay for postage stamps with credit cards, right? So that little component of meaning changes for free, as like that part of the meaning of postage stamp, I should say, changes for free when the concept of payment changes. And so we argued that yes, it's certainly important that there's lots of, like, grounding is certainly important for a lot of our concepts, but there's also a lot of our concepts which are abstract and relational, and like postage stamp here. And these are the kinds of things these are the kinds of relationships that we think are accessible to large language models, right? If you're only getting text, you can see that postage stamps tend to occur with things like payment and letter, and in certain relationships to those terms. And so if you represent those relationships, then you've really captured a core part of the meaning of postage stamps. Okay, so a quick interim conclusion here is that the success of large language models at doing language is I think, really hard to reconcile with the strong claims from mainstream generative syntax about symbols in particular, because there's, they're not symbolic theories, they're emergent theories like Elman's. And what I want to talk about next very briefly is just, could anything about symbolic approaches be right? And for this, I'm going to actually go back to another Chomsky example, which is this string pattern, A to the n, B to the n. So A to the n, B to the n just refers to this set of strings, AB, AABB, AABBB, and so on. Okay, so that's an infinite set of strings where all the A's occur before the B's, and if there's n A's, there have to be exactly n B's, so you have to match. So that whole thing is just called A to the n, B to the n. And Chomsky in the 50s actually argued that English follows a pattern like this. So he gave the example of if-then construction. So if it is raining, then you buy an umbrella. I could have two clauses. So I could say, if it is raining, then you buy an umbrella, then you will have a lot of umbrellas. And the key idea here, right, is that each if requires a then. So if an if is an A and a then is a B, then the first sentence is like AB and the second sentence is like AABB. And you could imagine, it gets hard to process, but maybe in principle our grammar kind of supports any number of these that you want. And if that were true, then you get A to the n, B to the n as a little subset of English grammar. There's actually a couple constructions like this in English. So either or is another one. And these constructions have typically argued, in fact, what Chomsky in the 50s argued for a hierarchical grammar. So for instance, I can write a little context-free grammar here. This just has a symbol on the left and a replacement rule on the right. So this says the symbol S, the start symbol, can be replaced with AB, or it can be replaced with ASB. And if you think through this, right, if I pick this one first, I'll generate the string AB, which is here. If I pick this one, I'll get ASB, and then I replace this S with this one, and I get AABB. And so however many times I pick the first rule, that'll generate, some number of A's, and then I pick the second rule to get the next one. And no matter what I do here in picking these rules, I'll always end up generating one of the examples, one string in this family. So right, this is a little hierarchical grammar that's maybe a tiny piece or something kind of like this is important for English syntax in these constructions. But that's one kind of argument, right, is to say, well, you get these kinds of patterns and I can model these with this symbolic grammar, and therefore people have this kind of symbolic grammar. You can actually give this to GPT if you want. So generate 10 unique sentences matching this pattern, AB, AABB, AABBB. It'll do it just fine. It's a little bit fun to play around with other versions. So if you just give it 2 examples, it now thinks that what's going on here is basically a repetition. So CD, CCDD is another example, or IJ, IAJJ. Or if you just give it 1 example, right, it gives you back, just thinks there are A-B strings. So from 3 examples here, it seems like it will generate the correct behavioral pattern, meaning the correct set of items. So the kind of key question, right, is does the ability to generate A to the N, B to the N sequences or whatever the pattern is, imply anything in particular about representation? And one of the things I've become very excited about recently is this old body of work, as I said, in the 1950s in computer science. There's this paper by Edward Moore called Gedanken Experiments on Sequential Machines, where he essentially thinks through the logic of when input-output patterns can tell you something about internal states and representations and what's there. So Moore has this kind of setup that actually looks quite a lot like modern cognitive science or something, where there's an experimenter who provides inputs to some device. They're called sequential machines, and measures outputs. And the experimenter's job is to just give inputs and measure outputs and come to some kind of conclusion about what the internal states and structures look like for this machine. So this I thought was remarkable, because he was designing electrical circuits, but for us, we're interested in doing cognitive psychology and have the same problem. Here's one of the key ideas from Moore. This is something which is proved in this context of inputs and outputs in dealing with some system which may have some internal states that determine how the inputs get mapped to the outputs. For any behavioral pattern, meaning any input to output mapping, there's a unique minimal set of states and state transitions that can generate it. And what that means essentially is that if you give me the input-output mapping, I can tell you, using an algorithm that Moore described in this paper, what states are necessarily present in order to generate that input-output mapping. And what necessarily present there means is actually quite strong. It means that any physical device which is creating this input-output behavior has to have something like those states in it. Could have more, right? It could have more states than the kind of minimal set, but it has to at least have the minimal set of states. So here's just a couple intuitions about, actually, maybe I'll skip this since I'm running a little bit low on time. We'll just leave it at that the set of states here have to be physically present, and the intuition is that if they were not physically present, you wouldn't be able to generate the correct input-output patterns. It's a little bit surprising that there's a unique minimal computational description of a system, but it turns out to be true, and it's an idea actually that's been used almost not at all in cognitive science, but quite a bit in dynamical systems theory, where people have been interested in coming up with kind of minimal versions of dynamical systems, and it uses logic that's built on Moore's kinds of analyses here. So here's the minimal state structure if you follow Moore's algorithm that's justified by processing A to the N, B to the N. Here's the start state, R0. I can get an A and a B, and then I go to an accepting state. I could get 2 A's and a B and go to an accepting state. I could get 3 A's and then 3 B's and go to an accepting state, and so on. So this is an infinite collection of states. It's not a finite state machine. It's a infinite state machine. But it happens to be the minimal one in the sense that you can't get by with fewer states than this if you're following that language, that string pattern. One intuition for this is that after I generate n A's, I kind of have to be in a different state for each n, because I have to generate next subsequently n different B's, and so my future behavior is really the thing that determines what state I'm in and how I'll generalize. There's formal versions related to this in computability theory, which I won't get into, but those essentially establish conditions under which, the set of states is finite versus infinite, using this idea that the core property of a state in this kind of analysis is as a determinant of future behavior. So you can actually look at this thing and if you spend enough time, you can come up with a correspondence between these states and the states of a grammar, or the states of something processing a grammar, like this A to the n, B to the n grammar. And so that's nice. You might think, okay, anything which creates A to the n, B to the n, must have a grammar. But I think as is known in the cognitive literature about that particular string pattern, there's a lot of work trying to teach it to animals and things. There's actually lots of different mechanisms that can give rise to this state pattern. So people argue about counting, for instance, essentially just counting A's and then counting down for B's. There's little computing devices like push-down automata, which can capture these strings, and they themselves have a particular set of states. So there's actually many ways to describe this particular state structure. So I guess I think of it as, in GPT, when it's doing this, it has to have a state structure like this in order to correctly generate those strings. And, grammars or push-down automata or counting might be appropriate descriptions of those, but there's nothing in behavior that can distinguish them, right? They all give rise to identical behavior in this kind of task. So these are all just kind of multiple descriptions of a single system. So if you think about this, this is, kind of a win and kind of a loss for cognitive science. The win is that sometimes patterns in behavior really tell you something about states which are present. And in particular, the minimal, in Moore's sense, set of states for a given behavioral pattern are states that have to be there in the system. On the other hand, our cognitive terminology is often a little bit underspecified in that we can often give multiple descriptions to the same collection of states.
Steve,
Yeah.
this is a good point. If you're still at the interim stage, there's a problem because you're not you came to Montreal, but you're going to go home empty-handed if you just continue.
Yeah, so I think I'll just skip a chunk here. I'll give you the two-sentence version, and I can wrap up in maybe 2 minutes, if that's okay.
Okay.
Cool. The conclusion here, right, is that patterns in behavior sometimes actually deductively imply a certain set of abstract states and transitions, and this applies to people and LLMs and symbolic systems and anything generating behavior, basically. This is the chunk I will skip here. I'll just say there's other work in the 60s showing how you could take an abstract description of states like this and come up with possible implementations of it. So sometimes you might have those states I just showed, but sometimes you might have two things operating in parallel or two things operating in series, which collectively have that state structure. And so there's, again, a kind of forgotten literature in computer science about how you can figure out possible implementations. And my argument would be that this literature is essentially what cognitive science should be handing to neuroscience and saying, look, behavior justifies this particular collection of states, and then here's all the ways that you could implement that collection of states out of simple series and parallel kinds of components. This is an idea that I've worked on in just a couple of domains so far. So I wrote this paper with Randy Galstel called Formalizing the Role of Behavior in Neuroscience that was on essentially path integration in ants and trying to make this kind of Moore-style argument. And then since then, actually, I've been working on applying this idea to a bunch of different domains, including grammars, number, logic, different kinds of memory formats like stacks and things. And so I have a book which is actually much friendlier than the paper with Randy, trying to lay out a bunch of this kind of history and put it in the context of doing cognitive science and connecting cognitive science to neuroscience. So this is the formal foundation of cognitive science. And if people are interested, I'm happy to share some early chapters. It's going to be an open source book from MIT Press, but I have early chapters on things like Moore's results and minimality and these 1960s techniques of figuring out what are all of the systems with a given state structure, and so on. So email me if you're interested in that. I'm happy to share it, and I'm always looking for comments from people. Just wrapping up here, patterns in observed behavior will sometimes necessitate internal structures isomorphic maybe to traditional symbol systems because symbol systems have the required state structure. And so from my point of view, like a lot of these things are still on the table, things like hierarchy, grammar, logic, and symbols on the table in the sense of the state diagram I showed, where there might be multiple systems with those state diagrams, but probably like the true system will share some of the states with at least some of what we think of for grammars or logic or symbols. This idea is actually very convergent with many ideas in connectionism. So Rumelhart and McClellan, for example, wrote that rule-based models may be more or less valid approximate macrostructural descriptions. So that you might be able to describe systems in terms of rules and symbols, even if they're implemented in neural networks, and that I think agrees very much with this perspective. Or Smolensky wrote that symbolic grammatical theory provides good approximations to the macrostructure of internal representations and functions. And so there's this idea of rules and symbols maybe being there at some level of description, but not being the kind of core underlying process, right? Like there's some other kind of emergent process which gives rise to them. Okay, so just to end here, every behavioral pattern necessitates a specific structure and latent states. This is a Moore result. Behaviors can't be produced otherwise. Calculus of this has, I think, been largely forgotten in the field, but I think it actually holds the key to understanding not just large language models, but linking these cognitive theories to neuroscience. And well-done symbolic accounts will propose formal systems whose state structure is minimal for the observed behavior. And the states of such a symbolic theory must be present in any implementation, so physical or neural or large language model. Okay, I will end there, and I'm happy to take questions and have discussion. Let me just thank my co-authors for this and related work, and a number of people who've had really important discussions with me that have really guided a lot of these ideas. So thank you.
Thank you very much as well. Exciting and informative. And now I ask everybody to please line up remotely by raising your hands, as Virginia and Anna Maria have done, and also here, levez les mains si vous avez des questions. And I'll start, and there will be lots of questions. So I'll start with Virginia, then Anna Maria, and then Rob Goldstein. Go ahead, Virginia.
Thank you. And thank you, Stephen, for the challenge that you provide to nativists. I have a question for you about symbols. I'm glad you brought them up. And I wonder to what extent you see the idea of symbols as compatible with what you've presented. Obviously, you do see it as compatible, but some people don't see it as compatible. So I'm wondering what you have to say about that.
Yeah, I mean, I think it's the common rhetoric in the AI communities these days is that these models have shown how symbolic stuff is all wrong. And, I think that there actually is a certain sense in which that's not quite right, but you can see how they got there, which is that the learning models work much better, right? Like, I think that large language models just work much better than symbolic learning models for grammar in particular, right? At the same time, those, like, what they are learning are not understood. Like, there's some internal states to those things which are mostly ignored by those AI communities, right? They care mostly about whether these things are useful or something, right? And they care less about the kind of internal functions. So I see this older literature as really in some sense, like rescuing the symbolic theories and saying, like, well, actually, like, sometimes behavior necessitates a certain state structure. And if that's true, then whatever is going on in those models, they have to at least have this collection of states. And if they do that collection of states, might be isomorphic to a collection of states for a symbolic grammar. Yeah.
I think the key word there is isomorphic, because that suggests, yes, there are such things as symbols that cannot be reduced to brain states. And so that's what I want to know what you think about.
Yeah, great. I mean, I think that's a very deep question. I don't have deep thoughts about. I mean, these quotes, kind of early connectionist quotes I shared at the very end there, their kind of picture of it is that all of the causal stuff is sub-symbolic, right? That, and that's true in large language models, right? Like the causal things are sub-symbolic, but on the other hand, the causal things are set up in order to mirror particular symbolic relationships, right? That's true in the A to the N, B to the N case. So I don't quite know how to think about that. Like, I don't think it's not kind of Fodor's special sciences version where he said the symbolic stuff just can't be translated into the low-level stuff, because I think it kind of obviously can, right? That's what's happening. But if you ask a question like where is the causal force in this system, it's not obvious to me that it's the symbolic side or the sub-symbolic side, right? It's more like, the training data or something led you to systems with a particular property. I don't know.
Okay, let's go on to the next question, and that's Anna Maria. The question should not be long. Go ahead. Anna Maria, you're going to lose your chance if you don't turn on your...
Okay, so I was saying, thank you for this presentation, which is not the question really, but the basic question is, what do you think about complexity? This notion of complexity, because it seems to be some kind of debatable, and also complexity with respect to what? What you presented is a system that goes back to the 60s from the generative grammar, where there's a lot of rule apparently, but there's no rules anymore. In 1970 with X-bar syntax, and today with minimalism.
Sorry, what do you mean by complexity? You mean complexity of a grammatical system, or complexity of a theory, or complex systems research?
Complexity about counting things, and that's what's in the first thing. And complexity about capturing generalization. So that's the second thing. I mean, the island phenomena that you discussed are just instances of structure dependency, right? Mm-hmm. So this is not only, it's one case of structure dependency. So how complex it is when you subsume a lot of observation under principles. And then semantic, okay? There's semantic compositionality, which subsumes in a certain sense lexical semantics, since it's generalization again, or relations which are cross-categorial in the semantics of the meaning of the word and the position that they are in a syntactic structure. And then more generally, when you think about the number of parameters an LLM has and their image of neural nets, complexity, and when you show a syntactic tree, which levels of embeddings, I'm not sure what complexity is, and I'm not sure we're comparing things at the same. I mean, it's certain that we have bias. All of us have bias, but in a sense, it would be nice to see a comparison which keeps things defined beforehand and then set. This is just a comment.
The question is posed. Go ahead, Stephen.
Yeah, so I think that among all traditions in linguistics and also traditions in cognitive science, there's people like the notion of trying to find simple theories, and there's formalizations of that in, for instance, minimal description length kind of approaches, which end up being equivalent to a number of Bayesian approaches, my critique of the kind of Chomsky approach, I think, would be that notion of complexity in that approach is informal, right? It's not formalized. even though there are tools like minimum description length and probability theory, which can allow you to have formal versions. So I actually think of large language models as probably doing a pretty good job at what is essentially minimum description length. So they have, yes, way too many parameters, but then they're configuring those parameters in a way which predicts upcoming linguistic data. I think it's widely hypothesized, I guess, that they can be compressed quite a bit. So it's often observed or thought that there's only a small number of units in a large language model which are relevant at a given point in time. And so probably if people worked hard on this problem, on the engineering side of this problem, we would find that you could compress them quite a bit. And if that were true, then they'd be in some sense a kind of ideal version of a linguistic theory, right? They'd be a kind of implemented one which was as compressed as possible. But that's work that I think hasn't been done yet. So it's just a conjecture or something that will be possible for those models.
Okay, thank you. Yeah.
Well, welcome back to Montreal.
Thanks. It's great to be here. So great talk, Steve. I'm really interested in a lot of what you're saying, and I didn't know about the Edward Moore stuff, but that's also the stuff that I found myself struggling to understand, and I have a gloss to try on you. I mean, because you talk about necessarily present minimal states, and to me, it's kind of misleading to think of these states as what you say they are, as internal structures, because they're not really there mandatorily at all. They're more like construals or interpretations. They're not functionally active. So I go back to like the philosophical distinction that I think Wittgenstein, then Kripke made about rule following versus rule governed. It seems like these states are explainable as rule governed, but it's not like the system is actually following these states. The thing it's following is the push down automata or the counting rule. So, and it feels like if you're going to be talking about a symbolic system, you don't want it to be actually following the dictates of those rules.
Yeah, I mean, I think this goes back to Virginia's question, and I'm not sure entirely how to think about it. I think that if you like when GPT is doing A to the N, B to the N, it's not following a pushdown automata, right? It's following the subsymbolic connections inside of it that are giving rise to that behavior. So I think it can be the case that you have those states, even though they're not the not like there's something causal underneath them that is determining the behavior. Yeah, I mean, I'm not sure how to think about it other than that in the LLM or the neuroscience case, right? Your intuition is that that's not right, that there's that they're really following the rules of a pushdown automata instead of the substrate.
I think that's exactly what I said. So I think of it, the state description that you're giving is an interpretation, it's a construal, but it's not causally active. What is determining the behavior is the algorithm of the pushdown automata.
Even in an LLM, you would say that?
Yeah.
Oh, wow. Okay. We should talk more because I'd be really interested to hear your thoughts on this. I have the opposite intuition, which is that the causal thing is the implementation, right? It's whatever that big neural network is doing. And the pushdown automata is a description that we attribute to it. It's one of many descriptions you could give to that collection of states.
Well, yeah, but either the transformer architecture or the pushdown automata, neither of those are your derived description of the states, though.
Yeah, right. So my states would correspond to a clustering of the vectors in a transformer architecture. So I guess in that sense, right, it's the maybe what you're saying is that it's not the transformer itself that's causal, it's the abstract state description or something. And actually in dynamical systems theory, that this formalism is in the dynamical systems theory version of this formalism, the states are called the causal states because they're the things that determine the future behavior. Is kind of what clumping of the underlying system is relevant to determining future behavior patterns. So.
Okay, good interaction, and now I give it to Mike.
Okay, two things. Just briefly, I don't see why you claim it's modern language models that refute Chomsky's approach to language. I mean, they were refuted long before that, and it's a real confusion, I think, between Chomsky, who is looking at language in human brains, and we refute him by looking at language development, and how do children acquire language is something I'm very concerned with. And let me just use one aspect, your postage stamp example. I fear that most of the students here have never seen a postage stamp. But certainly for those of us who did see postage stamps, we didn't think about them in terms of your definition. We first got them because we saw things arriving in the mail, and we saw these pretty pictures on the corner. And so I want to distinguish very much the embodied experience that you ignore and the way in which, as we master language, we can master more and more complex descriptions. The large language model is given a zillion of these sentences, and on that basis can give things that no child could give. So I think that any thoughtful account today of how children acquire language refutes Chomsky. We don't need large language models, and they are totally different from, I think, what the brain does in acquiring a language. But I want to go back to your reading Moore's paper. I perhaps am the only person in this chat who first read it 65 years ago. And in 1961, I published a paper called Finite Automata, Neural Nets, and Turing Machines. And the point is, I think follows on Goldstein's point, is that coming up with the minimal number of states for a finite state machine, and then coming up with an equivalent McCulloch-Pitts network gives you two different structures. What is the minimal number of neurons is different from the minimal number of states. And then let's add the fact that this depends on the minimum number of states. Theorem was about finite state machines, which is the lowest level of the Chomsky hierarchy.
Yeah.
And I think I'd better stop there because I fear I could go on for several hours.
Good points. Your turn, Stephen.
Yeah, great. So the first point, I don't think it has been widely accepted that Chomsky was refuted by these previous studies. I mean, there's certainly lots of people who have believed that and who have kind of argued against it. There's also lots of communities, lots of people in linguistic communities who have continued to work in Chomskyan traditions. And my take is that it's been a little bit unclear because neither side here has had a very good model of language. So there hasn't been a very good formalism which can deal with all of this syntactic complexities that come up in language until large language models. So I think once they started working very well, my take is that they really showed how a different set of principles can do a good job of explaining language. And, those principles include things like embracing probability and being good at memorization and integrating syntax and semantics and these kinds of things which are not part of the Chomskyan tradition. You're right that they are almost certainly different in form than the neural realization in language, and they're also quite different in acquisition patterns, right? So they get 1,000 times more data or whatever than a kid does. But I think that has led some, including Chomsky, actually, to reject them outright and just say that these have nothing to do with language because they get so much data. And I think that's not the right angle. So I think it's not right, in part because current models have been made by AI companies who aren't really interested in learning in 1/1000th as much data, because they already have all the data that they can use. So my guess is that as people kind of more explore the space of network architectures and things, my guess is that it will turn out that there are other architectures which can learn with considerably less data, maybe using other data sources like video or audio or whatever. These things probably will speed up acquisition in some way. So there's been this effort called Baby LM to try to do this, to try to train something like large language models on less data and maybe using multimodal data, and it's only been going for a year or two. But my guess is that it will get us closer towards real life acquisition. And sorry, you had a third point, I think.
Oh, never mind. It's just, well, for example,
Yeah.
minimal. Let's go back to the question
Yeah.
about minimal.
Michael,
Like-
I can't let you do it.
Okay,
what I'm gonna say is that Steve, we'll get to Larry who gets the last word here, but Steve, you should write this up as a target article in behavioral and brain sciences, because we can't need this feedback, and you'll get it that way. We can't give it in a seminar like this, unfortunately.
Yeah, sure. Yeah, it's a good idea.
Go ahead, Larry. Sorry, Michael, go ahead. You've written your target articles already. Go ahead, Larry. Lawrence Malone.
Microphone.
Okay, I can't, we're out of time anyway. I want to thank you very much for an extremely stimulating talk.
Okay.
And it's not over until it's over. Thanks a lot.
Awesome. Thank you again for the invitation and the great questions and discussion. If I missed anybody, feel free to email me, or if you're interested in seeing the longer form of this, these arguments, I can send the book draft. So thanks.